I think we are recording. Yeah. Okay. Welcome to the week 3 live session of this course, Intro to Machine Learning. So I was planning to do today the questions of assignment 1 and 2 because their deadline got over. So I guess we can discuss their solutions. And I understand that there is some confusion in some questions and all of that. We can handle that today. Does that make sense? Okay, so we'll start with the first assignment. So any thoughts on this question? So which are our classification tasks? Finding the gender, predicting price, predicting whether there will be abnormally heavy rainfall this year, and predicting the number of copies of a book that will be sold this month. So A and C are the accepted answers. Anyone who has any doubts in this? No? Okay. Uh, is it is so can someone confirm if they're able to see me or not?
Yes, sir.
Okay. So Abhirup, maybe you might want to leave and join again. Maybe that's an issue. Just try it out. Okay. Um, So yeah, I guess this question is a bit straightforward. So A is finding the gender of a person because gender is only male and female, at least in the context of the question, right? And predicting whether there will be abnormally heavy rainfall next year. So whether there will be, that is the keyword. We are not trying to understand what will be the rainfall, number of centimeters or whatever, right? That's not the question. Whether there will be abnormally heavy rainfall. So that becomes a classification task, yes or a no. Yes, there will be abnormally heavy rainfall, or no, there will not be abnormally heavy rainfall next year, right? So that's the way. So hence it also becomes a classification task. Yeah. Okay. A feature F1 takes certain values A, B, C, D, E, F and represents the grade of the students, and which of the following is true. So F1 is an ordinal variable, right? So anyone who has a confusion here?
No, it's nominal plus ordinal, right?
I'm sorry.
No, it's a nominal variable, right? Normally we say ordinal means named plus ordered, right? So it should be both of these.
So basically, when you say so the more correct answer is ordinal, right? So ordinal, this could be the right answer. You're right in saying that all ordinal are nominal, but we so actually it's more like categorical. So I would just make that distinction. Uh, this is correct. So let's say categorical. This gets into two, like nominal and ordinal. So I guess what you're saying is all ordinal are categorical. That is true, and all nominal are categorical. But nominal, when you say you explicitly tell that okay, there's no order among them, right? So ordinal is the right answer. Yeah.
Actually, we got confused with that option. The fourth option was there, right? Both. That's why.
Oh, right. Yeah. No. So I would say it's more ordinal. Ordinal is the right answer. Yeah. Anyone?
Okay.
Yeah. Anyone else has a question? Okay. Let me just assignment one. Okay. Then yeah, the third question. Suppose I have 10,000 emails in my mailbox, of which 200 are spams. Uh, okay. So how many of you got the answer A? I mean, okay. Anyone who has not got the answer A can help me understand what was the issue.
Sir, can you please solve this problem, sir?
Sure, no worries. Yeah, let's go ahead and do that. So so for these kind of questions, again, I would say, just always draw the conversion matrix. Okay. So let's say this is the true label. Okay. And this is a predicted label, right? That is the two rows and columns of a conversion matrix. And what we're saying 10,000 emails in my mailbox, right? So total is 10,000. So this is 10,000 here, right? Total column sum, row sum, everything together, right? Out of which 200 are spams. So we know how many are spams. Okay. So this is, let's say, true spam and true not spam. Okay. Predicted spam and predicted not spam. Okay. This is what we are trying to understand. So, this is what the conversion matrix, contains. So we're saying 200 are spams for sure. So this is 200 here. So then how many will be not spams?
800.
What is the total number? 10,000, right?
8,000. Sorry, sir, 9,800.
9,800, sir.
9,800, right? This is the true not spam. Then we are saying the system spam detection system detects 150 emails as spams. So we're saying that the spam detection system, it predicts or detects 150 emails as spams. So 150 goes here. Total we are saying we don't know how much is the distribution between these two, right? Then the next tells you that there is out of which 50 are actually spam. So out of 150, 50 are actually spam. That is this column. So remaining is 100, right? Then so now you can fill actually the whole table. 200 minus 50, this is 150, right? 9,800 minus 100 is 9,700, right? This is going to be 0, 5, 8, 9, right? And this sum is 13,000. So all good. Now, what have we asked? We asked precision and recall, right? So anyone want to tell me what recall is? Who has their mic open? Yeah. So if you want to answer, you can go ahead and answer. No problem. Sindhuja, do you want to answer the question? Only then unmute the mic. Otherwise, you can mute. So anyone want to take what is recall supposed to mean? So basically, recall is so the word recall also you can use it to understand what recall means. Recall means basically, are you able to get the facts back, right? So out of actually true, let's say, how many were predicted true in some sense? True in the sense, actually the class and predicted or whatever, right? So here we are talking about spam detection system. So for us, spam is a big concern. So actually, how many are spam? 200, right? How many are predicted spam? So among them, how many are predicted spam, right? Among the actually ones that is true, that is 50. So this becomes 25%, right? Is that, yeah. Now, precision is kind of the opposite. In precision, what we are saying is how many were predicted to be, that class, let's say predicted true. That's the denominator, total predicted true. Okay, let me just call total actually true. Among them, how many are predicted true? Total predicted true, how many are actually true? Among in this particular case only, right? So total predicted true or predicted spam are 150. This is the total of this column of this row, right? Because it's a predicted rows. So in this spam is this row. So 150 are predicted total predicted spam. Among them actually are just 50. So this is 50. So this becomes 33.33%. So hence the answer is A. Okay. So any doubts, any questions here?
No, sir.
Okay, good. So fine. So this is about the third question. Fourth question, which of the following statements describes what is most likely true when the amount of data, training data increases? So any doubts here? How many of you say A is the right answer? And if there are people who disagree with the accepted answer, you can raise your concern.
This we had lot of confusion, sir, actually, in this question. Finally, we saw the answer.
Okay, so at least according to me, the answer is supposed to be B. So I have written to the NPTEL folks, but so the idea is this, right? Whenever the amount of training data increases, so your training error usually decreases as usual, right? Why? Because you're training the model to do better on the training data set. So your training error will obviously decrease. Now the point is, because you have more amount of data, right? You might be able to capture the patterns much more better. I mean, that's the thought process. So you might do better in the generalization error also, right? So you will have a decreasing training error and decreasing generalization error also. Okay, so four, at least according to me, B is the answer. But let's see, let's wait for them to confirm. Okay, anyone who disagrees can raise their concerns.
Can you once please explain what generalization error means?
Right. So generalization error is basically how does the model perform on unseen data, right? So generalization error, right? So error on unseen data. So this basically, again, we can use the example of the child learning example, right? So because we are training the model using the training data, so it's possible that the model can just by heart all the question answers, right? Just like how a child could, do that. But so if we actually want to know that the child has learned or not, the best way to understand is to give questions which the child has not seen before, right? So hence the idea is something that the model has not seen, unseen data in the sense something that is not in the training data. You want to check what is the error on this unseen data. So if it has low error on the unseen data, that means it has learned the concepts or the patterns well, rather than just memorizing what was given to it, right? That is the idea of generalization error. Now, ideally, I mean, hopefully what happens is if you increase the amount of data that the model can look at, that is amount of training data, it's possible that the model can actually learn, can see more and more patterns and hopefully do better on the unseen data. Is that?
Yes,
Sir,
thank you.
one more thing, sir. Here, I mean, whenever a new, sir, imagine the training sample which was earlier given and learned, it has some error. I mean, when we give a new set of data to the training sample, I mean, new sample is given. Probably model may initially have a training error which is more, and gradually it becomes constant or something. Right, sir. In most of the graph, it is shown like this only. So the training error, I mean, finally, when before applying the validation test, probably it would have undergone through this graph. It may not, I mean, finally, before doing validation, the training error could be less.
Correct, that is true.
So it is confused. This answers is really confusing, sir.
Graph shows from that graph itself, if you see with training set increase, the training error is increasing, like overfitting is happening. So usually won't C be a good option?
Yes, sir. Even I put actually C only.
No. We're talking about the question number 4. In question
Yeah,
number 4.
correct. For in general trend also, I felt C is better.
Okay.
So in general trend, we see this kind of curve which is shared in 5. So
Yeah,
with
even I.
training, there will be overfitting beyond a point. So,
Again, see.
oh no. Okay. I'm not sure.
That's confusing, sir. All the three. I mean, somewhere it looks everything matches.
Yeah, I think hello sir. I think most of the people have selected C. At least that is what I see in our discussion forum.
It's
Yes.
B
That
or
option
C.
C was
Yes, sir.
selected.
Yes.
It's B
For
or C,
number 4,
but
is it?
not A for
Sir, for 4C,
C.
training
Yes,
error
sir, for
increases
4C.
initially and generalization error usually decreases.
Okay, so but why would that be? See, I try to understand this. I mean, I'm trying to understand the thought process because see, just imagine, let's say I give a child only 3 questions and answers versus I give another child, let's say, 6 questions and answers, right? So, training error in that is basically we measure by saying, okay, among the samples that you saw, are you able to do well or not? Right? Then because the amount of training data has increased, training error generally will keep on decreasing, right? Because you basically just get more and more samples, so you are able to learn the data well. But generalization error will decrease. Is that not the thought process?
Sir, may or may not increase, sir.
Uh, so
Generalization error.
generalization error
Sir,
will
but
decrease, but
Hmm.
training error I'm not getting like
sir, but
it
in the
will depend
lectures
up,
also
it
it
will
was
depend
taught that
upon the
training error
model
is
parameter.
independent of the size. Yes, it is dependent on the model.
Model, exactly. If
That is
model
true.
parameters are such that it is high, means high non-linearity case, say, for example, then it will overfit and training error will reduce. But if the model is less degree polynomial and we are fitting in little bit haphazard data, then there will be training error more. So uh, I don't get directly how we can generalize and say training error will decrease or increase with uh, the increase in number of training set.
So I agree with the point that yes, more training data you might not. I mean, it depends on the model complexity also.
Okay.
But
Sir, what I understood from this question is model complexity remains constant, either because it doesn't speak anything about model complexity here.
right.
So without changing model complexity, if we, for that model,
Hmm.
if we keep on increasing the training data, then
Hmm.
what is the error?
No,
So if we keep on
there
increasing training,
there is a direct relation actually. If you're giving a training data which is haphazard, cannot be captured by that model's parameters, then training error will decrease. And if you are giving data such that with that lower complexity model you are being able to capture better, then training error might decrease. So uh,
my
two types
like
of things can happen.
right, but at least that are some boundary conditions where training error might have some issues and all. But what at least my understanding was is if the training data is valid. So if because if for lesser training data, if we kind of train the model, then it is like overfitting because training error is very less. Then if you keep giving more training data, let's consider it as a normal condition where it is valid training data. If increasing the training data, then actually training error should kind of increase because now it is having more and more samples. So it is not fully
Usually,
overfitting. And then generalization error will decrease eventually because if lesser number of training samples, it's kind of overfitting where training error is less, but test error is more. With more number of training data, then it kind of it can generalize more. That is
So,
one of the
so
principle.
Bhavani, if your model complexity is low and you're giving more training data, which is cannot be captured by that model, then
Hmm.
training error will increase.
So if model complexity is low, then
Low,
more
and
both
you're
will
giving
both
that cannot be captured data which cannot be captured by that model, then your training error itself might go bad.
so
So
like
basically, if you take a linear separation and non-linear separation sample space, if your model is linear and you're giving uh, data which is non-linearly separated, so training error might increase with with a linear model.
Right, but here I'm not considering a low complexity model, because then bias comes into picture where both will be more. Training error will be more and test error also will be more. So that in that
You're
case,
keeping model
uh,
parameters as constant. Now you're assuming it is low or high. That is also a question.
no, but here when they did not mention anything about low or high, we should consider a kind of a better model, like with a right parameters. So here it doesn't specify.
By better, there is a still a assumption. If you're
mm,
Right.
if you're taking nth degree model and you're feeding in, that cannot be solved by nth degree polynomial. If the sample space you're giving as n plus 1th degree, that can be solved by n plus 1 or greater, then it's still going to train badly. Training error will increase. Did you get what I wanted to say? Even if you're uh,
Okay, like sorry, might be I just joined in between. So what is the answer you are suggesting, Abhiru? Because in
so
I'm
it
seeing.
can be B or C. It depends upon the model and the uh, type of data input set you're giving to it.
Mm. Okay.
Yes.
Okay, one second. Bring it back. So I understand both the point actually. So it does depend upon the model complexity that we are assuming. Under that, how it will go. So let me get back to you with the right answer. This what they thought with while keeping this into their minds. Yeah.
Okay,
Is that
But it is definitely not A, sir. So it should be something
sir,
different than A.
It's not
right?
A.
can I give my interpretation of why A is correct? Okay.
Sure, go ahead.
See, uh, assume, let us say there is a correct hidden model inside the data. Okay. If you give large amount of data, that means the data is highly biased towards that particular model, right? The data is getting generated out of that hidden model only. Whatever is the model, we don't know. Okay. Whatever data we are getting is coming from that model only. So if you use that huge amount of training data, actually we are making model complex. That means we are making the model highly biased towards the training data.
No. Okay. Okay. One second. So, you're right that there is a model which is generating the data. It is so a true model, right? It is not right to say that the data is biased towards the model, or that true model is biased towards data. That's not technically right, because the idea is we do want to know that model at the end of the day, right? So now the point is, if with some with some method, if you can get as much data out of the true model as possible, right? Now what will happen is you can understand more and more patterns from the data. So ideally generalization error will never increase if you have more amount of training data.
That's correct. Because see, if you have a lot of, suppose you are given some X amount of training data, what will you do? You will try to minimize training error. You have not seen the unseen data. So
Right.
if your attempt is to decrease the training error and the consequence is increasing generalization error, you are defeating the purpose.
Right. Correct.
I mean,
Yes.
it is totally counterintuitive. Unless you reduce the training error to such an extent that it overfits, then you can assume that it is generalization errors increase. So this is a very a fuzzy answer and a fuzzy question, which is very tough to interpret.
Right. Yes, I get your point. So my thought process here is basically whenever you give more data, the idea generalization error decreasing is, I would say, non-negotiable in some sense, right? Because you have access to more patterns, hopefully, and therefore you'll be able to do better on some unseen data. And why training error usually decreases in the sense, and again, this is from the point that because the model is asked to train on, do well on the training data at the end of the day, right? And so either I increase the amount of training data or decrease it. Ideally, the point is the training error usually has to decrease because that's what you're trying to optimize for at the end of the day.
Yeah.
Right. So hence,
I guess
give the right answer. But I get your point, that it could be dependent upon the model complexity, etc. So hence, so let me do one thing. I'll get back to you on the right answer and the exact explanation for this. Is that fine?
Okay, that's fine.
Sir,
Okay.
I guess it is more of like if the model is complex enough, then the training error is will obviously decrease. And if the model is not complex enough, then the training error will increase.
Good increase. Yes, that's true.
So
Okay, good enough. So let me just put that here. Right. Next question number 5. I saw there are a lot of questions here also. So you
Yes.
train training algorithm, plot the again sort of similar sort of issue. The following figure is obtained. So so as you see here, the idea is that as you increase the training set, that is you have more and more training examples. So the test error is decreasing, which is, let's say, good. But the training error is increasing, right? Um, so so what do you think the algorithm is suffering from?
lower complexity,
Even this is difficult, sir, actually.
high bias
Yes.
because of
No,
lower
I
complexity.
would say I have written the answer C, which has come out to be wrong.
Yeah,
Right.
Yes,
even
sir.
Because
Even C seems to be wrong because initially in the starting, if the training instances are less, it seems to be high bias, and when it is more, then it is high variance. So they're not asking about which region. They're asking about the whole graph. So doesn't seem to be like a correct kind of question where it is
but
asking
whenever
exactly
you
what it
talk about
means.
One sec.
whenever you
So
talk about training error, it means on the training data, isn't it?
correct.
So if the because you know what in the tutorials at video at around 31 minutes, there is a table plotted which says that there is bias variance, number of features, number of parameters, and number of training examples. With the increasing bias, it says that the number of with increasing number of training examples, the bias remains same.
Mm.
That is what the video says at 31 minutes. But then that is in contradiction to this graph.
Right. So okay. So okay. So can you all agree that B is not the right answer at least, or do you? Does
Yes,
anyone
sir.
have a
yes, sir. Yes, sir.
I agree with
B
you.
is not the right answer. Even I
B is
Yeah,
say.
it's not the right answer
correct? Yes, because
because nothing can be.
as I'm getting more examples, my
Yeah.
test error is decreasing. That means I don't have a high variance model, right? Is that correct?
Yes, sir.
You may have a high variance, but it is not depicted by this graph. Because if it overfits, then you may have high variance.
No, but we're seeing here that as I increase the number of training examples, the test error is decreasing, right?
Okay. Yeah.
है ना?
Yes, you are right. You are right.
हाँ, so, so it can't be high variance. Now, my
Yeah.
contention is it's ideally high bias model because then because the point is if your training error is increasing, then it means it's not able to learn the simple patterns also. That is basically characterized by having a high bias model.
Okay.
This is the condition I was telling at. It can
I'm
happen in
sorry.
the I was telling that
Okay.
previous question pe same thing can happen.
Right.
So that's why C is also a possible answer, I said.
Right. But yeah, I mean, they have made it. I mean, the question says most likely and all of that, so it becomes a problem to quantify all of that. But okay, I'll get that this one.
Sir, so how should be the ideal curve?
I'm sorry.
How should be the curve for an ideal model?
Ideal model is basically you will not increase in training error with at least with respect to the training set size. So training error will sort of remain same because you can learn the basic patterns easily. That's the thought process, and then because you're seeing more and more examples, you're able to capture more and more variations in the data, and therefore your test error should decrease. Yeah.
So training error should
Sir,
be
can you
very
repeat
minimal, right?
whatever you said just now?
Right. So I would expect something like this is what I'm saying. So something like, so your training error will sort of remain same or might decrease for a while, or might decrease, but the test error will surely show a, you know,
Decrease.
Training error, and the x-axis here is the training set size.
This is any model should behave like this, right, sir?
Right.
When it learns.
Hopefully, yes.
Then
Correct.
in this case, there is no bias or variance, right, sir? In your graph.
Right. So there is no bias because we are able to do well, similarly on the training error, and the model doesn't have a high variance. I mean, it has high variance in the sense that, okay, if I don't give a large amount of set size, it will be erroneous. But I can solve that using a more number of examples. That means it's a high variance model, all right, but I am able to solve that using a large number of training examples.
Sir,
So
but for high
actually,
bias, right, sir, the training error also will be more, right, sir? So because that is what at least we have learned, I feel, from the class, that whenever it is high bias, both will be more. Training error will be more, test error will be more.
no,
So,
but my question is, does test error have anything to do with the bias? Nothing, right? They're two different things. Test error has only to do with variance.
Mostly, no. I mean, it does depend, right? Because let's say if your example, I mean, if the model is simple enough and there are only simple patterns in the data, your test error will not have that much effect. So it does get affected by both the factors, and we will see that today actually in the bias-variance decomposition.
Okay.
Yeah. So I mean, these are all a bit subjective, but I would say that high bias basically means a high training error, low test error, and high variance means high test error and low train error. Sorry. Yeah, correct. Okay.
Sir, repeat the second one. A high variance, you said something.
So if a model has high variance in it, right? What this means is it will have high test error.
High test error. Okay.
Right. And
or low bias. Yeah.
Low training error.
Okay,
Low
sir.
training error.
And yeah. Similarly, opposite for high bias system. Right. So test error will be generally low, but the training error could be high.
Okay, sir.
Yeah. So again, I understand it's a bit subjective, but yeah, this is what it is there. All right.
Sir, if we see the notes, right, sir, like which is shared in the week 1 notes, page number I think 70, sir. So there it explains, sir, like whenever it is high bias system, which is like underfitted, then both will be more high training error and high test error. So that is what is, and whenever it is overfitted,
Right.
then it means it is low bias and high variance. That time, low training error and high test error. So
page
whenever
number
there is,
That's why C should be correct answer.
yeah, that
it is
is what
neither.
That's what I.
C should be the correct answer. That because as per given in the notes.
Question, sir, has actually taken our time. Because most of the options look correct.
Sir,
when
actually,
we read
right?
it again and again, it's confusing.
Got it.
Question 5 answers question 4, sir. Because it is like the 5 is showing the graph and 4 is just an explanation. And both speak the same thing.
Correct. No. The issue is the most likely statement. You can't quantify that well. But okay. Anyway, I put that to to the NPTEL folks. Let's see what answer comes up. Yeah.
Okay. Thank you, sir.
Okay. So yeah, let me just.
Sir, just a second.
Hi, William.
Go ahead.
Sir, so as per your thoughts, what will be the right answer for the question number 5?
Question number 5, according to me, it was high bias.
Is it a
As
case
per the
of underfitting or a high fitting? What case there is false? This model is about underfitting or it is a case of high overfitting? First, we need to find out. This will happen when there is underfitting or when there is high overfitting.
See,
What's the case here?
no. So this is neither, because of the fact that underfitting may you have both errors are very high.
Right.
Right. But here what is happening though, right? Here the test error is decreasing, but the training error is increasing. So it's neither case.
So
And
C should be
generally,
the answer.
this is very rare. I mean, this you will not get unless you have some huge issue in your model. So because the point is you're trying to solve for the training error. Your model is trying to solve for the training error. It's trying to minimize the training error. So you will not be. I mean, you will not see this sort of curve, generally. But yes, this is neither the case, because underfitting may you have both errors are high. In overfitting, the training error is very low, but the test error is very high.
Yeah. So C should be the right answer.
But underfitting and overfitting, underfitting and overfitting are predominantly determined on the basis of test data. Is it correct?
No, both. No, both the training data and the test data, because you will see you will try to understand how much is your training error compared to your test test error compared to your training error. You need both of them to be able to quantify in what phase the model training is, basically.
The combination can be either it is high bias and low variance, or it can be a case of low bias and high variance. But the given case, if it is underfitting, then it can be high. It has to be high bias and low variance. And in case of overfitting, it has to be low bias and high variance. But here the options are given are high bias and high variance, which is not possible in any case. So I think C should be the right answer, because it is neither a case of underfitting nor it is a case of overfitting, and any model has to fall either in underfitting or underfitting. It cannot be even in the best ideal model. I think this won't be the case that it has a high variance and high
This
bias.
discussion never ends, sir, actually.
So I think C appears to be the best optimal answer according to me. I think.
Right. Okay.
As per given this situation.
Fine. So I've taken your arguments into consideration. Let's come back to this question in the next
Right.
week. Yeah.
Okay. Thank you.
Make sense? Yeah.
Yes.
Okay. Right. So moving to question number 6. Any questions here? So
B, I think.
Right.
Unsupervised and supervised.
We are talking about clustering. So clustering is clearly an unsupervised problem. We don't have anything to learn from. We just have to look at the patterns in the data and training separate models to predict something. So that's basically a supervised problem. Yeah. So that's the B is the right answer. Question number 7. B is the right answer, not A. I've already mentioned that to the NPTEL folks also. And the a lot of things that you guys spoke on the group also was fine. So accuracy formula is basically TP plus TN, right? All the places where the model is correct. So the model is correct whenever it is true positive and true negative, compared to everything, whatever is there in the whole table, right? That is basically sum of everything. So accuracy has to be TP plus TN divided by this sum. Okay.
So it is B, right, sir? Correct answer. 1 and 3.
Yes, the right answer is B. Yeah.
Sorry, you're talking of the question 7?
Yes, question 7.
Yeah. I'm just looking at my score sheet.
Yeah.
There it is written accepted answer is, I have put B. It was got a score 0, accepted answer telling A.
Yeah. So I have mentioned that to the NPTEL folks that the right expected answer is wrong. So they will change it to B, and once it changes, it'll show up in your scores at that time.
No, it is not corrected.
Sorry?
I'm just checking it out. Along with because score has that quiz paper, I'm just matching. I mean, what you are saying, whether it is correct or not. With the explanation.
Sir, I feel the definition of precision, true positive by true positive plus false positive
False
is correct.
positive.
That is the only thing which is correct. I
Yeah,
feel.
true positive and by true positive plus false positive. The precision
Yes.
is that.
So A is correct. That's what I feel. That
A
that
is
number one
correct.
is correct.
No. Once again, the options
No.
are these A, B, C, and D. So you need to select among these equations which are all the correct ones.
So precision and recall 1 and 3 is the correct answer.
Correct. That is option number B, right?
Option number B, yes. But it was put as 0 here in my score.
No, 1 and 3 are correct. 1 and 3 are correct. That B is correct.
1 and 3 are correct. That is option B. But I put option B, but it has been given a wrong answer, score 0. But actually, they have stated accepted answer A. But what sir is saying, it is they made a mistake. It would be the B is the correct answer.
Yes, it will be corrected once they go through whatever their procedure is to change these answers. This one, right?
So the score sheet will be reviewed once more.
Yes.
If their answer is correct, wrong. Okay.
Yes.
Doesn't matter.
All right. Eighth question. Anybody? Any thoughts?
It's a A.
Right, straightforward, right? And all of these are basically machine learning problems because we need to understand from the data what are the patterns. Data to understand the pattern, anything, right? It's just straightforward application of different algorithms that exist. Okay, which of the following is with overfitting? Yeah, go ahead. Who all wants to take this one?
See the B, D, and I think F. I put it was a partial scoring. E is not. E is the answer is also to be considered. What has been said. The good performance on training data overfitting.
B, D, E, F is the right thing.
B, D, E, F. I put a B, D. I missed out E, so it is a 1.5 instead of 2.
Yeah. So any doubts on why E is not the right answer according to you guys?
No. E has to be there. I mean that is. Okay. I missed out. That's different.
Right. So I hope all agree on that the right answers are B, D, E, F, which is the accepted answers, right?
Right.
Okay.
High bias doesn't means overfitting, right? No. High bias.
Overfitting means low bias and high variance.
Low bias.
Yeah, low bias and high variance overfitting.
High variance is the overfitting.
So again, overfitting is basically on low bias and high variance. These two together.
Okay. Yeah, you're right. Because the training error is low in overfitting. That's why it is low bias.
Right.
Yeah.
Agreed.
Taken as a.
Now I got this correct, but I forgot.
Evaluate models purpose in the training.
Okay. Question number 10. Any thoughts?
I thought A
mistake. It was got a 0 here. I put A.
But the correct answer they said is D.
D.
Well, I think both are correct, frankly.
No. So again, cross-validation is not used to evaluate a model's performance on the training data. For training data, you already have the training error with you, right? To evaluate the model's performance. So you can always use a training error to understand how well the model is doing on the training data. You don't need to do cross-validation for that.
You know why I put
a simulation of the test phase. Yeah, that is a cross-validation. So D is correct.
See, the reason why I put A is that at about in the video, Professor Sarkar has drawn a diagram in which he has divided into training and test data, and training data is divided into training and validation.
Right.
So I thought that you have to improve the performance using training and validation, which is a part of training data. Therefore, I felt that the cross-validation is used to evaluate the model's performance on training data.
Don't worry, I also made the same mistake. I got a
You get what I'm saying?
No.
That is the video.
Yes, he's right. He's right.
Trail of the video.
The video.
What is the A is correct?
Yes. According to the video, the A is correct. I also agree.
No. So the point is cross-validation as an algorithm to understand how well it will do on the test phase. Now, because we don't know what the test data is, ideally speaking, because that happens post validation. So what we do is we say, okay, I will take the training data itself and I will remove some part of the training data and treat it as a test phase, and we call it we call it as a validation data, right? And we
Sir,
do that
one thing,
whatever.
this validation is with the training data only. Test data is outside, I think. But what has been taught to us?
That is correct. So hence we simulate the test phase. It is not, we don't get the test data at any time. We simulate the test phase.
Simulate.
Okay,
So
we'll
the
take the
data will
part
be okay. Yeah.
as tested.
So D is no doubt correct. D is no doubt correct, but I thought even A is also correct. A and D.
No. A is not right. No, A is not right. Very clearly not right, because always evaluate the performance on training data with the training error.
Actually, what my understanding is, suppose we have some data set in which, for example, 80% for training and 20% for test. Am I right? That 80% data set used for training can be iterated with a different validation. For example, it has to be divided into k-fold, out of which k minus 1 set should be used for validation and remaining for training. Am I right?
Right.
So,
According to
sorry. So k minus 1 fold you will use for training, 1 fold will do for test validation. Yes. Yeah. Go ahead.
So then C is the right answer.
Yeah, C is the right answer.
C.
Yeah.
But C is saying that it's applicable only to classification problems and not regression problems. Why do you think it's not applicable to regression problems?
No. I'm not talking of 10. Sorry. I'm talking of the 11, because here you are talking of the K fold. So that
Once again, I haven't gone to question number 11. Question number 10, no doubts, right?
Question number 10, D is correct. Or D is the right answer.
Right. Anybody else have any doubts on question number 10?
No.
Okay. Yeah. Question number 11, what you were saying is C is right. Yeah, C is the right answer, no?
C is the right answer.
What does cross-version involved in machine learning? Parting it into K subsets, evaluating each subset as a validation set, while the K minus 1 is for training. That's right. Any thoughts on this? Anyone disagrees?
That's right.
Okay. Question number 12. What does the term feature space refer to in machine learning? We discussed this extensively, I think last to last video.
Yeah, it is for the input variables only. So I think the C is the right answer.
Right. So it's only about input space. Feature space means only input space. Space where output predictions are made by the machine learning model is the target space or prediction space, whatever. Right. That's different. And together, when you use it, it's called instance space, because you're talking about both the input and the output variables together. Then let's question number 13. So which of the following statements are true regarding supervised and unsupervised learning? Yeah, C and D. Need any has any other thoughts?
No.
I think perhaps there can be a case where supervised learning can be applied on unlabeled data also. Is that not possible? A is not. I think A should also be included in the answer.
No. So supervised learning is basically only for labeled data. Self-supervised learning is purely on unlabeled data, which is sort of like unsupervised learning. Semi-supervised is basically labeled and unlabeled data.
Sir, why can't D also looks like a valid answer? Unsupervised learning means basically it is a clustering, right? Clustering you can interpret as finding patterns or groups
in the
C
data. C and D both are correct.
It is accepted, right? C and D both.
C and D, yes.
Okay.
C and D both. Yeah. Okay. One of the ways to mitigate overfitting is
decreasing the complexity.
By making the model less complex, right?
Yeah.
So amount of trained removing is not going to help, right? Again, as simple thought process, more data you get, you are able to learn more patterns. Therefore, you will not go into overfitting. And by adding more features, the problem is you need more and more data to be able to make good estimation of your patterns. if you have more features. So by adding more features, you actually can go into overfitting. All right, then this one, how many Boolean functions are possible with n features? I guess this also we covered in the first class, I guess, but
yeah, A.
A is the right answer. Anyone has any doubts here? You can ask.
Okay,
No?
it's
So the
understood.
quiz course has been separately given.
I'm sorry.
The assignment score.
Yes,
Assignment
it has
score?
been released. Yeah. The progress report has been released here for this assignment 1 and 2.
Sir, the 15.1 Boolean functions, I can understand 2 to the power of n, but can you just explain the workout?
Okay. Anyone want to try out their hand here? Question 15, assignment 1. The answer is 2 power n. So who someone wants to try why this is the right answer? I mean, almost all of you agreed with this one. So
I can give it like
0, 1, and then again 0, 1 to the power n number of features. So
Correct.
2 to the power n.
I'm sorry.
It's a Boolean function.
Okay, so Boolean
So
function.
0, 1.
Yeah.
So there will be 2 is the base, and that will have a n features.
N features. Okay. So
Each feature can take 2 values, either true or false.
2 values. So
the total number of permutations that will be possible is 2 n and
2 to the power of n is, I understand.
Yeah.
2 to the power of n is possible permutations of the input data with the binary.
Right.
Yeah. And the base is binary, so 0, 1. So that is a 2 to the power n.
It's basically Boolean function. So if there is 2 to the power n in sample points, you can the hypothesis space is made up of how many possible functions like that. Each point you can predict as 0 and 1. So it's number of instant points into means each can be 0 and 1. So total it will be 2 to the power n.
Okay, sir, got it.
Yeah, so Boolean function, basically here it means that your input and output both are basically Boolean values, right? So both can take only zeros and ones. Now each row basically here is when I have, let's say, 1 to n features. So how many number of rows in this table, that is basically 2 power n, right? Now when so now to define a function, to define a Boolean function, I need to define the complete table of this, right? So what is the output for this particular combination? What is the value for this particular combination, and so on. So now one particular way of defining this output is one such value for each of these n 2 power n rows, right? So I can take 0 or 1 here. This row again I can put 0 or 1 here, and so on. So I have 2 possible values per row. Number of rows is 2 power n. So therefore it becomes 2 power n. Okay.
Yeah.
Fine. So this is question, sorry, assignment 1. Assignment 2 will go now, and yeah. Question number 1. Yeah. So yeah, we did this entropy and everything in detail last time. So any thoughts? What is the first question answer and why?
Actually, for Vig, the number of Y's are 2.
Okay.
And out of 2, the emotion is one is sad and one is happy.
Okay.
So equally distributed. So entropy is 1.
Entropy is 1, right? That's it. Very simple. So Assignment 2 question 1 is the same formula that we have been applying for last time, right? So proportion of positive, log of proportion positive, proportion negative, log proportion negative. So here you can take anything positive, negative, that's fine. But yeah, but you will get this as again log base 2 as I confirmed last time. So you will get answer as 1. Yeah. Okay, so A is the right answer. Entropy of emotions given years equal to 3.
So the answer is okay, and I have a doubt. Number of years 3 means
3 means
what? Years.
Can I give the answer for this, sir?
Sure, go ahead.
There is only one record which is 3, and it is positively classified, and it belongs to only one class. So the entropy value is 0.
0. That's okay, but number of years can be 3.
Yeah, we have here, no? So number of years to all are 2, but only one
Logically,
row has...
logically speaking, what is?
Oh.
Yeah.
Correct. That is true. Logically speaking, it is not right. Okay, so help me. So, but we can have some deformities, right? Sadly,
Okay.
That is one possibility. Other possibility is, I mean, you're right in the logical sense. The point is, see, any feature in ML algorithm, whichever you have, can also have some noise in it, right? So it's possible that the number of years, for example, the person who was writing this number of years for this particular person, right? Let's say, so then he was sleepy or something, and he pressed 3 instead of 2, right? So I mean those kind of noise, like which you cannot have any control for. You cannot even imagine those sort of noise can be present in the input feature space also. Hence, these things are possible, and yeah, but the point is that with numbers equal to 3, apparently people are all happy if they are 3 years.
Maybe I would interpret this way, sir, because there is only one entry with number of years is equal to 3, and it certainly says happy. That means there is no uncertainty. If it is 3 means you can say 100% is happy. So there is no uncertainty. So entropy is 0.
No, that is correct. That is correct. The question here was, how does it make sense to have y is number of years equal to 3, right? So one reasoning for that is, okay, there could be some deformity. That is fine. The other possibility, and this is something that you should get used to, the idea that it's not possible that all the features always are noiseless. Even the features themselves can have noise, and the labels themselves also can have noise. So this is possible that because of some noisy input, it became 3.
What exactly is the meaning of this word noise?
So basically, that is something that there is some randomness that affected the value that you got, right?
That means some irrationality.
Irrationality, yes. You can
irrationality embedded in the value.
It is embedded in the value. Yes, that is correct. So whatever you measure from the your feature value that you get, it has embedded in it some irrationality or noise in it. Yeah.
So every data point will have some noise.
Yes, you should
if
always.
There was no noise, there would be no error.
Sorry.
If there was no noise, there would be no error.
Not true. It depends upon how your model is, right? Because then you get into the inductive bias and those sort of issues, right? Those can have errors at the end of the day. But the point is, if let's say your model is exact model as the data that is generated, right? If there was no noise, then you might be able to do very well. You might be able to get the right, zero generalization error. But there is always some inherent noise in the features or even in the label that you have.
So here the correct answer is B.
The correct answer is B. Yes, 0 entropy.
Here it is given. Correct answer is A.
I'm sorry.
What the screen you are showing here is showing it is a correct answer is A.
The question number 2 we are discussing right now, right? Question number 2.
Yeah. Yes. There it is B. Yeah.
Okay. Then which attribute should you choose as a root of decision tree? Anyone have the values that you have tried to compute for these?
Color. Actually,
Sir, actually, I got an information gain more for wig rather than color.
Or is it?
Not where I went to.
Okay.
Others.
So anyone who has tried out the the final values, if you have it.
I tried out. It is coming out to be color.
Okay.
And color is quite higher than the other two.
So assignment 2, question 3. So how you will do is basically you will say for the root node the entropy will be 5 by, so yeah, so it's going to be minus 4 by 9 log 4 by 9 minus 5 by 9 log 5 by 9, right? This is the root node. Malathi, can you? Yes, please. Thank you. So if you use color, for example, you have how many children? You'll have one for blue, one for green, and one for red, right? So you'll have 3 children in this when I use this node. So you will have, you need to take average over these values, right? So then for green, the entropy is 0, right? Very clearly. Red entropy is 0. Blue entropy is 1, right? One sad, one happy. So whatever value you get here, let's say this is A. So A minus, here the average will be 2 out of 9, right? 2 out of 9 into 1. So this is going to be A minus 2 by 9. Is this correct? I mean, you can just verify this. Then wig have children, only yes or no, right? For yes, the entropy is high, it's 1, literally, right? So A minus average here is again 2 by 9. So 2 by 9 into 1 plus some value. And you can actually see here, it'll be some positive value. You can see here that color is already increased, is more than this wig, right? Because I have some positive value here. And then similarly for number of years, right? It'll be again A minus. So 3 is 0. So I have this is 8 by 9 into whatever entropy you get here. I think it's again going to be 1 because it's right. So highest that you get will be here.
Color.
Color will be the answer. Then question number 4. In linear equation, the output is continuous, right? This is very clear. Yeah, 5th question. So what is the answer according to you guys? Question number 5.
Answer is B.
Actually, I could not understand how to solve this, but just like that, I have put B.
Okay.
That answer is correct. Just I want to know how it has come.
Okay, sure. Let's go through it. So assignment 2, question 5. So I have X and Y. And 749. Okay. So now what are we saying? We're saying that the way we have taken a hypothesis h theta of x equal to theta naught plus theta 1x, right? And we have defined the mean square error to be this value. There is j theta of whatever, this one. Now here, if theta equals to 1 comma 1, so what does this mean? What is theta equal to 1 comma 1 in bracket? What does this mean actually?
It means I think beta 1 is equal to 1 and beta 0 is equal to 1.
Right. Okay. So basically, when we this is basically the vector notation of the parameters. That's it. So theta equal to 1 means this is theta naught comma theta 1, right? So this becomes, so theta naught is 1, theta 1 is also 1, right? So now basically what you need to do is you want to find out what is h theta of xi, right? So h theta of xi in the sense all the different x that you have. So I'll just write x here. So that is basically whatever 1 plus x, right? Because that's what it is. 1 plus 1 into x, that is 1 plus x, that's it. So this becomes 7, 6, 11, 4. And then what you need to do, you need to take minus yi. So subtract these two, okay? So 0, right? And then you need to square each of these values. So you'll get 0, 4, 4, 0. And then, so this, what you're doing is we're looking at h theta of xi. So for each x, what is the h theta that we're getting? What is the output of the hypothesis function that we have? Subtract that from the true value, the true measured value, that is y, and then take the square, and then take the average. But not average. You take 1 by 2m of that, right? So add all of this, you'll get 8. And 8 by how many values do I have? 4 values.
4.
2 into 4 is 1.
What is the last figure, that column?
I'm sorry?
Last column?
This column?
Yeah.
This is the h theta of x minus y squared. This is h theta of x minus y.
Square.
Right? This is what it is. So when you take sum of these values, that is 8. The sum is 8. And then you take this sum divided by 2m. Right? The sum by 2m. M here means basically the number of training examples. There is 4 I have here. So 8 by 8. That is
Sir, why we are taking h of x is equal to 1 plus x?
Because
it is given.
right, so we are asking, so basically what we're doing here, we are asking, okay, what is the MSE if theta equals to 1 comma 1? This is exactly what it is saying. If theta equals to 1 comma 1, find j theta. What is the MSE? So if theta equal to 1 comma 1, what does it mean? It means the values of this theta naught plus theta 1x. So h theta of x now becomes 1 plus x, because theta naught is 1, theta 1 is 1.
Okay, sir.
Exactly. Okay. Okay. Question number 6. Is B the right answer? How many of you agree that A is that A is right answer? Let's say that B is not right.
Sir, I feel none of the algorithm will give us an optimal result.
Why? So
Guaranteed. The question is guaranteed, no, sir.
Right. I mean, that's one way to answer such questions. But okay, so what is the logic behind it?
Because the function is very simple. It might not consider all possible, since the training data is too low. So the very low means the bias is very low, and therefore chances of getting overfit is very rare. Chances of underfitting is high, I think.
No. No, I get your point in that sense, but this is not really asking that question. You might need to think a bit more to find the logic behind it.
Training data is less likely to overfit.
We are on question 6. Let's just stay there for a while. So the ID3 algorithm is guaranteed to find the optimal decision tree. So optimal decision tree finding, is it so ma'am said something about it, like, is it possible to do that or not, first of all? Why do we go to decision tree algorithm in the first place? Why are these algorithms used?
For
Easier
classification.
Representation will be easier.
Right. Okay. I mean, yeah. In comparison to others, this one that's fine. I mean, so if you remember, ma'am said that optimal decision tree is you cannot solve the problem in NP. So it's basically NP hard problem, right? So what we do is we take a greedy approach at every step, right? So we are now taking we now do this inductive bias sort of a thing. We say, okay, I want to choose shortest trees, right? So basically, get me as low depth trees as possible, and hence we said, okay, we have this preferential sort of bias in the inductive space now. and with that, and the way to obtain shortest trees is to use a greedy approach at each node, and hence we came to this idea of information gain, Gini index, all of those, right? Because what they're trying to do, they're trying to give you at every step what is the best that you can do, right? But it may not be true that overall it's the best. We don't know that, right? That is a difficult problem to solve. So rather what we do is we use a preferential bias, and in that so how do we quantify that preferential bias is by using this information gains or system. So I would suggest, going through the first few minutes of this decision tree lecture. There ma'am tells about all of this idea, right? Okay.
Yes, sir.
Okay. Fine. Next, a classifier trained on less training data is less likely to overfit. I guess we're
more likely to overfit.
Yeah, right. So the right answer is B. And whether the following is true. So overfitting is likely when the hypothesis space is small. Is that true?
I found this to be true, but the answer is wrong. You know why I felt this to be true? Because suppose you have only 2 points, okay, and you are doing regression. Obviously, the hypothesis space is very small because you have one linear fit, and therefore that is an overfit, but which can prove to be dangerous when you do on the test data. So when the hypothesis space is small, you are more likely to overfit. On the other hand, there's a possibility you have too many training points. And for every training point, you can have n plus 1 polynomial which can fit n data.
So you're confusing.
Therefore, there are two extremes.
So hypothesis space is not dependent upon the training data as such. Hypothesis space is basically the space of all functions that you want to use or use as your model. So linear regression is a simple hypothesis space because we have only linear relations and that sort of a thing. So the kind of functions that you choose to search from, that is a hypothesis space. There's no relation with the training data at all. So training data and all of that comes in when you're talking about overfitting, because now, so when you say hypothesis space is small, it means the model is simple. I can represent the model using a simple sort of a function. If it's a simple function, then its overfitting is less likely. Right?
Okay.
Yes.
So if you have substantial amount of data, then there is a great chance that you can have a very complex model which will overfit and a simple model which will not overfit. Therefore, since your hypothesis space is large, you are more likely to overfit, and therefore the converse is true. That means overfitting is more likely when the hypothesis space
is
when
small,
the hypothesis space is small. Small means you have got very few models.
Yeah, therefore B is
you have very few models, and therefore it is overfitting.
Therefore, it is less chance of overfit. Therefore, it is underfitting rather.
So there's a danger here of underfitting when you have space being small, because you don't have enough complexity to capture even the actual patterns also. That's the real danger when you have hypothesis space being small. Okay.
Hypothesis space means both input and output, right?
I'm sorry.
Hypothesis space means both input data and output.
This one, so that is the instance space, right?
Instance.
We clarified this thing last time. So it was a feature space is basically only features.
Yes.
Output or target space is basically what the outputs are supposed to come, and both together is the instance space. There is one instance, one instance of your example or whatever. Hypothesis space basically all sort of functions which you are allowing to search yourself for.
All the algorithms.
No,
right.
nth degree polynomial you can take as hypothesis space you are increasing when you increase the n of the x input vector. Correct, right?
But it is only on training data, right? Hypothesis space is only on training data.
No, it's upon the model parameters you are setting. So basically, hypothesis space, if you keep increasing the n, basically if you're reducing the n, means you're creating bias. Basically, hypothesis space means you can have how well you can capture that in the training data. So if your model parameters you're purposefully putting say second degree polynomial, but you're actually the data is in say fourth degree polynomial, then it's a problem. So hypothesis space is like how well you will be capturing. So if you're reducing the hypothesis space, then there is chance of underfitting. So if you're increasing, then it is overfitting. Okay.
So hypothesis space small means you have less complex model, because you can't fit so many. You cannot fit a more complex function in that, right? That is meant by hypothesis space being small. Large means you're able to model even complex functions also. That's the idea. So when you have a larger hypothesis space, which means you have more complex models, then you have overfitting is more likely, right? So, but here the question is opposite. Therefore, the answer is false. Is that clear?
Yes.
Means we have simple models, therefore overfitting is less likely.
I'm sorry?
You have simple models, that's why overfitting is less likely.
Yes, correct. If you have simple models, overfitting is less likely. Underfitting is more.
Okay.
Okay.
Many a times these questions look like legal interpretation of the Constitution.
Sir, exactly, I agree. I agree with the colleague's
Whether
statement.
Article 370 is constitutional or not constitutional, I'm listening to Kapil Sibal's arguments. It sounds like that.
We can interpret in either way, sir. So I agree with that, sir. Sir, maybe one source where you can explain with beautiful examples, overfitting, underfitting, bias, variance, training error, test error. My head is really turning. I can interpret it either way, as sir said. Now, any good source is okay, because I'm actually been reading it. More I read, more I'm getting confused. With some example anywhere, you can set some material.
Vector algebra background.
It's like sir, Raj sir tell this is correct, then yeah, probably yes. It looks like that. Some questions, sir.
Okay, so let me take this as an action point on myself. Find a good source for discussion on this overfitting, underfitting, etc.
Underfitting,
Last
bias, variance trade-off.
Last time you were to talk about measures of bias.
Yes, I have that today.
Okay.
And I was hoping to complete this early,
okay.
but let's
yeah, and also training error tester, all are related.
Correct. Yes, they're all related. That is true.
Raj, I think so. Vector algebra, any course will be the base point, starting point.
Testing error.
Because somewhere we are missing some important point, something like a switch.
So this is put on vector space, so vector algebra base is required.
And no, sir, we need some intuitive feel first, then mathematics later.
No, mathematics is not required. If you study that vector algebra course, that basics, I studied it like during my master's 8 years back. I have only intuitions left. I am being able to understand with that. So once you need to understand in depth, then intuitions will remain. If you want to do religiously, say.
Okay, fine. Yeah. Okay. I get your points. So let me come up with a source which can give some intuitions and also deal with the math if interested, right? So as to justify those intuitions, why they should be right. Yeah. Okay. Fine. Next is question number 9. Any thoughts here?
Sir, it is computationally expensive, right, sir? I mean, when we do a multi-way split, and why it is not the correct answer?
Okay. But why do you think it's computationally expensive? Because let's say if I have multi-valued, if I do, for example, let's say some node A, and then I have, let's say, 4 possible things versus, let's say, same A, but I have 5 possible things. When I have to compute the values and everything, it is just I just have to compare the value of A with these 4 and 5, right? So why will that be computationally expensive? Searching is, and that too, this is a sorted. You can have a sorted list, so you can do like binary search, all of that. So it's not expensive to compute these values, to compute the final outputs of all of that.
Okay, okay, sir.
Right. So, but okay. So, how many of you don't agree C is the answer? Okay.
Sir,
So,
hello. Sir,
yeah, go.
I think that it's not, but the concept says that it's real valued.
Right.
Real valued input. So if it is real valued input, so we can have large number of data, right?
Last number of data.
So as
Okay.
you said that, so our if I branch for 4, if I move from branch 4 to 5, that doesn't make sense. So it's key. It could be large number of input. So why it would not be A answer? Because it's becoming computationally very expensive. So I am not able to capture all the input.
So again, so the point is, see, when you have to choose a branch among, let's say, even 1,000 or 10,000 values, or even 1 lakh values, the point is, because these branches, whatever they can be ordered. So therefore, whenever you want to understand, okay, which node should I go to next, that can always be done very fast because the data is ordered. Point number one. Point number two, searching is less of a concern here, right? So you can always get the right node easily. Again, this is not something that is a concern. Searching that to an ordered list is not a huge concern. Yeah.
Normally, the binary split is simpler than the multi-way split.
Hello.
Right. So it is simpler, right? So.
And
is it like since it's a
The
real
computation will be
input?
expensive, but it will not be too expensive.
I'm
The
sorry?
expense will be now what she says that it will be too computationally expensive. That is not the case. The complexity will be increased. There is a marginal difference in computational cost.
Correct.
That's why A should not be the answer.
Right.
I think.
So it's not too computationally expensive. That is correct.
Sir, what I mean to say that, so it is real valued input. So
right.
If it is real valued input, so how can I capture all the inputs? So maybe every time, every new example will have a new value.
Infinite.
It's quite possible.
Okay.
It's quite possible.
Fine. Yes. Agreed. So okay. So let's say so basically okay. So you will learn the decision tree from the training data at the end of the day. Is that correct? Right. So let's say I have n number of training examples. So that means I have at max n unique values. Is that correct?
Yes.
For this feature. Now, because they are real valued, I can order them. If I have an ordered list, I can search in the ordered list in log n base 2 amount of time using something called as a binary search.
Yes, sir.
Now, let's say if this n is basically, let's say 10,000 or something, versus let's say even if it is 1 lakh, the amount of time that I need to, that will increase between these two is not that high. And when I say not that high, we are trying to answer this question in terms of let's say the order of the order of complexity that you will need to change, because the order here is order of log n. This is not a big deal to solve.
Yes, sir.
Sir, but at every node we have to compute this information gain and other parameters, right, sir? So
correct.
But again, that is also log function actually.
Right. So the point is, once you do the multi-way split, see again decision tree learning we're talking about. So once learned, then what is the point? Then what problems exist? After that, there's no point of computational expensive, because it's a log n based sort of algorithm that you need. Yeah.
So this is a real value, right? We will have only n number of points for that, but real
Correct.
space is infinite space. So on test data, anything from that can come and we will miss that.
Right. That's exactly the point of the option number C, right? Because you have seen only n possible values from those huge number of possible values. So then because the test data, so on the test data, it's possible that you will see something else entirely, because of the fact that it is a real value input attribute. So hence you will not do well in the test set, but you will do very well on the training set. Okay. Is that clear? Okay. Which of the following is true for decision trees? Any thoughts on this? Anyone disagrees with the answer is A?
No, the answer is A. Decision trees are interpretable. Decision trees they're not resistant to overfitting, and decision trees they're suitable for regression also. So not just binary classification.
Right. Okay. So yeah. Then question number 11. What is the following? Which techniques can be used to handle overfitting? So answers given A and C.
Pruning.
Sir, I have made A is correct, but they have not given marks for that.
Yes, sir. Even I mentioned only A. For me, I don't know why C is correct, sir.
C
Yeah.
even I have, sir. A and D I felt.
Right.
But not C.
Okay. So we all agree that A is one of the right answers.
Right.
Yes,
correct,
sir.
sir.
Okay. Then increasing tree depth, does it handle overfitting?
No.
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 It
Right.
increases overfitting.
We want a shorter bias.
Right. Yes. So we want shorter trees to handle overfitting. Fine. Now, decreasing the number of samples required to split a node, is that going to handle overfitting or increase overfitting?
Handle overfitting, because it's a stopping algorithm while creating the model.
Correct. But we're talking about decreasing the number of samples.
So that is not right.
No, okay, decreasing the no. Okay.
Sir, what I feel is like here decreasing. So it means you can also define how many minimum number of samples should be there in that internal node and decide if you have to split or not. So
Correct.
if we let's consider if 100 is the minimum number. So if whenever if that node has 100 samples, then we have to go for splitting. And if you decrease now from 100, if you decrease to 50, so it means you are again. So when it reaches 50, then you are kind of splitting. It means it increases overfitting. So it doesn't reduce the tree depth, but if you decrease the sample size of that node, then it increases the tree depth, which eventually increases overfitting, right, sir? That is why I didn't feel C was the right answer.
Perfect.
Same here, sir.
Right. That's the right explanation, because the idea is if you decrease the number of samples required to split a node, that means more and more nodes become eligible to get split. That means you will keep on you will have higher tree depth compared to if you increase the minimum number of samples. Now from option B, we already know if you increase the tree depth, you will have higher overfitting. So I've already written this again to the NPTEL folks. So ideally the answer is only A. And D again is a general question. More features to the data set. Any ML algorithms will require more data to not overfit. So if you just increase the number of features, you will end up overfitting. Okay.
Okay. Okay, sir.
Okay. Which of the following is a measure used for splitting the best?
Just a minute. So according to you, C is not the correct answer. Only A is the correct answer.
Only A is the correct answer. That's correct.
Okay. Oh.
Yeah. Okay. Yeah. Question number 12, Gini index, and yeah, remaining we'll probably do in the coming parts of the lectures. But yes, only Gini index is one of the things that is used to split in decision trees. What is the purpose of decision trees root node in machine learning? Again, option B, right? It starts as it's a starting point for tree traversal during prediction, right? It doesn't determine the stopping criteria. It contains the feature of the training set. No. It represents the class limits of training data set. Also no, right? It basically represents one feature on which you will start your whatever prediction
Splitting.
time splitting. Okay. Which of the following is true about linear regression? Both regression and classification, no. Not affected by outliers, again, no. Can handle missing values, no. By the way, decision trees can very easily handle missing values, right? Because that can just become one of the branches in the tree itself. For example, let's say there's some feature which has missing values in the training data set. Then what will happen is you will just say, okay, just make a separate branch and for basically all the values which are missing for that particular feature, right? Whereas linear regression cannot handle that sort of a thing. It needs all the values to be present because we do this sort of multiplication with values again. So beta times x, you keep on multiplying and get a final value. And this is clear. It assumes a linear relationship between the independent and dependent variables. Question number 15, which of the following can be used to mitigate overfitting? Any thoughts here?
Sir, A and C, okay. Even D is a part of it, sir.
I'm sorry?
Sir, the answer is A, C, D given. Even D can be used to mitigate, sir. Is the answer correct? That feature selection or dimensionality reduction?
Yes. So the idea here is when you do dimensionality reduction, you're going from a higher feature space to a lower feature space. So then what happens is, because the features reduced, again the same idea comes here. This question that we had here, adding more features. So in some way we are reducing the number of features. So when you reduce the number of features, you tend to not overfit. Yeah. So feature selection and dimensional reduction is one of the ways to mitigate overfitting.
Okay, sir.
Okay.
Why gathering more training data?
Yeah.
15C, why?
We already spoke, right? Because when you have more data, you can learn more patterns. So hopefully you will have less test error, which means you're not overfitting, right?
Okay.
I had a question because I missed initially assignment 1, question 1.
Assignment 1, question 1. Okay.
Yeah.
Yeah.
So, since D is a integer variable,
right?
Y is an integer, so
right.
Shouldn't this be also classification?
No. See, again, number of copies of a book that will be sold this month. Ideally, you expect this to be from 1 to infinity. It's integer, all right, but so it's 0 to infinity, right? So you cannot have a classification algorithm. Rather, you will do you will take it as a regression problem, and you will say, okay.
Actually, in one of the lectures, he said if it's discrete, it's basically classification. If the Y target variable is discrete, then it's a classification problem. So it's a bit dicey. This is discrete, right? Like not 1.5 or something like that.
Correct. No, correct. So again, discrete, but it has to be finite possible values.
Okay, finite. Okay.
Yeah. because I mean we don't assume it to be in at least in the current formulation we allow even infinity to be a in so we take it as a regression problem.
So in first question, first A is okay. Find the gender of a person by writing style. We can classify whether male or female. Right. But in the C, we are predicting only. No, it is not classification.
So we are predicting, all right, but what are we predicting though, according to you?
So whether the heavy rainfall will happen next year or not.
That's exactly the statement. Will happen or not. So it is just yes or no. So it's a classification task, right?
Oh. And then the B also can be the classification, right?
Why?
Price of the house.
So price of the, so it can be, let's say 1 lakh rupees or 1 lakh.
That is a regression.
It's a regression problem. It's a continuous random variable at the continuous variable that you have at as a target, right?
Okay. Okay.
Yeah. Okay. So this is week 1 and week 2 assignment questions. I've taken down, the questions that where we have doubts. I'll get them clarified, with ma'am and Pitel folks.
Sir, and when to expect, sir, those answers, like next session or might be in the discussion forum?
Yeah. So,
those questions which you'll clarify.
So I'll try to put in the discussion forum itself, so that next session we can do something more different. I mean, move forward with the discussions. If not, and then if you have any doubts, we can discuss that in the next session. So I'll mostly put it on the discussion forum.
Okay. Thank you.
Fine. Okay, so shall we go ahead with the next topic for today, the bias-variance decomposition? I thought to do that because some people wanted to understand the math behind it. Shall we do that now, or if you want, we can do the any doubts if you think you have in the week 3 lectures. Otherwise, I can get the. I mean, we can do it in the Monday, Tuesday sessions of TA.
Okay, let us have that bias variance. It is always something fuzzy. So if you can explain clearly, then that will be better.
Sure. So, okay, let's do the bias variance decomposition, also generally called as trade-off. Okay, so again, Malati, can you mute yourself? So people who are not speaking, just mute yourself. Okay, bias variance decomposition. So let's say I have some x. Okay, consider an x in the feature space. Okay, and then I have some data with me, right, which I use to train my model, which is basically like this, if I'm not wrong. So I have n such examples, right? This is a training data set. Now what we assume in general machine learning is that this training data set is a IID, that is identically and independently distributed sample from the joint distribution of x and y, right? X are your features and y is your target value that you want to predict. Okay, so this assumption you need to understand. Then let's say for this particular x that I have with me, right? So let's say I make a measurement on this y, on y for this particular x. So let's say I can write that y as f of x plus some epsilon. Now this is where you need to understand this f of x is the true function. Okay, true function which takes this x to y. Okay, so you can imagine this to be something like, for example, let's say you have some temperature sensor. Okay, temperature sensor. it will use whatever, your surrounding, heat or whatever to understand what temperature is, and it'll give out a value, right? So the true functioning of this is f of x, but as we already know, any system in the world is not perfect. This will have some noise inherent in it that is captured by this epsilon variable. Okay, and what we assume additionally is this epsilon variable has zero mean and has some fixed variance. Yeah, zero mean and fixed variance. So why is this? You have to understand why this is a required assumption. Is you're saying that on an average, whatever you measure, this is what you get out of the data, out of the sensor. So this is a measured value, right? This is a true value. This is a measured value. So what we're saying is on an average, your measured value will be same as true value, right? So we are saying that the temperature sensor is not that bad, but it has some noise in it, right? Which is true for any real world system. Okay. So now when you okay, so now as you already know, when you have this data with you, you use this data set to train your model, right? And let's say I will call that model as f hat, right? And I've used this d data set to learn this function f hat, right? So f hat of x comma d is the prediction for this x that I have with me, right? This is the prediction that I make for x. Now help me understand, is f hat a random variable or not?
It is not a random variable, sir, because it is what is predicted. I mean, based on the model, it's a predicted value. It is not random.
Okay. Any other thoughts?
Since x is a random variable, output will be a random variable.
Okay, so let's consider x as fixed. You will not take x as random variable. Okay, so if x is fixed, then is this a random variable?
So what is D? What is D?
D is a training data set. So all the points that you have with you, right, to train a function, to train whatever ML algorithm, that is f hat, right? That is D, training data.
There will be randomness in it. There will be randomness in it, but it won't be a random variable.
What has randomness in what? Sorry.
In the prediction for x would be some x plus some randomness plus noise.
Plus noise.
Yeah, some
in your prediction
randomness.
Have noise, is it?
In your prediction.
Why?
Because there is noise in the there is noise in the data.
In the data. Okay, you're coming close there. So noise in the data is there. But why? So you're saying that D itself is random.
D is also some element of
I'm
randomness is there.
Why you consider x as a fixed? That is a variable in any case.
No, we'll take x as fixed for now, and then we'll see how to incorporate the randomness in x also. So for now, consider x as fixed. Some value in the feature space. Yeah.
Then f hat is not random. It will also, if that is a fixed value, a real value, then f hat will be also not random.
Okay. So here, Bhushan was close to it. So the idea is this D that you get, right, is itself a random sample. Right. So we discussed this idea before. I mean, a bit not in this detail, but we spoke about this idea where we said, we do training, validation, test, split, and all, right? What we said, okay, we'll take some 70%, 15%, 50%, and so on, right? So 17% when you take, sorry, 70% when you take, this 70% is a random sample of all the values that you have with you, right? So in a sense, the training data is basically a random variable, which is from this space, the XY space, the joint XY space. Okay, so therefore what happens is whatever f hat you learn, that depends on this random sample, right? Because if you change d, the learned function also changes, right? So hence whatever d has, because d is random, f hat also becomes a random variable. Is that clear?
Okay.
Right.
Okay. So the inputs to the function are random. Therefore, the function f hat is also random.
Input in the sense of what?
D.
So okay, d is not the input to the function. See, function always takes x as the input, right?
Okay. Yeah.
So
but x is also random because d is random.
Sorry.
X is random because d is random.
Again, x is not random. No. This is not what. Yes. Okay. Let me give you one example. So in linear regression, right? We assume this, right? F hat of x is, beta naught plus beta 1x sort of a thing, right? Now, if I give an x to you, beta naught plus beta 1x is not random. It's a fixed value. You give one x, you will get one value out of it. That is correct. But you're learning this beta naught, beta 1 from where? From the data set. Training data set, right? Now, because the training data set is random, this becomes random. The parameters become random.
Okay.
Right? Because the parameters are random, so the function becomes random. But every such function, every such random function that you can get is a deterministic function, because if you give a single x, it will give you a single value.
Okay.
Right? So f hat is basically a random variable of where it's over a space which is basically a set of all deterministic functions. Deterministic functions of that whatever form that you have chosen, right? Linear regression is like this. If you have decision tree, then it's a set of if and if else rules sort of things, right? And or not, whatever, right? That sort of a thing. Okay. So hence f hat is a random variable. Are we clear on this?
Sir, beta naught and beta 1, they are the ones which dictate the model. So they are now becoming random variables. Because beta naught and beta 1 random variables, we say that function is a random variable, right?
Correct. Yes. Because the way you learn beta naught and beta 1 is from the training data set. Not the training data set itself is a random variable.
Okay.
Because hence this becomes a random variable. Is that clear?
Yes, the function is random, not the x. Yeah.
Not the x, correct. That is not in our current formulation. Okay, fine. Okay, so now okay. So now the idea is I want to look at MSE. Let's say my y is a continuous random variable, and how we do in linear regression, we look at the MSE value, right? So now when I want to do MSE, I will do between these two, y minus f hat of x given t squared. Is this correct?
Yes, sir. Yes, sir.
Yes, sir. Yes, sir.
Right. So because see, I don't have access to f of x. F of x is a true function that exists in the nature. But at the end, the temperature sensor or whatever sensor is going to give me y. It is some noisy version of this true function. So at the end, what I have with me is y only, and I have a fitted model on this data set D. So for this particular x, this is my MSE. Okay. Now this MSE is not well defined because so many things are random. So what we'll do is we'll take the expectation over this, right? What is the expected error, expected MSE for this, x that we have here? Okay. So I will take the expectation over what variables? Anyone want to take a guess? What are the variables over which I would take this expectation?
Over y and x?
Over y. Will I take over x also?
D. We are going for D.
D hat.
Sorry?
The predicted value.
For D.
D.
For
D hat.
D and?
For training error, it will be D, and for testing error, it will be x minus D.
No. Again, we're talking about any point. We're talking about any x in the feature space. So it doesn't matter if x is in the training data set or not, right? Why will that matter?
It is for P hat.
See, at the end, whenever I have an x, I will pass it through this function f hat, because that's the model that I have built, that I have learned from the training data set. So whatever the function is, that depends on the training data set, which is random. So the expectation has to be taken over the data, over this random sample, that is D. And what else is variable here? Any thoughts? I'll keep this.
On y alone, sir. Y.
Sorry, sir?
On y.
On y. That's good. So on y also I can
Y and D.
Sorry?
Y and D. Y and D.
Why on D? Because see, the MSE I want to calculate. I want to see overall possible, this training data sets, right? Because that dictates what my function is.
Yeah.
Right.
No,
so,
I said Y and D, not Y on D.
Sorry. Yeah, Y and D, correct. Now, the randomness in Y is coming from which part of the equation? Only from epsilon.
Epsilon.
Hello. Who is? Please yourself if you're not talking to the class.
ஆமா ஆல்ரெடி உள்ள அந்த செகண்ட் வீக்ல உள்ளதை இப்போ பண்ணிட்டு இருக்கேன்.
All right. So so we basically have this yeah, so y and d. Now the point is y variable as such, it's random because it has this epsilon in it, right? So I can just take the expectation over d and epsilon. Is that fine? So taking randomness over over y is same as taking the mean over this random variable epsilon. Is that correct?
Yes, sir.
Okay. Now with this, what we will do is we will break it down into 3 components, and then we'll look at why it comes out to be that. Then this I can write it as we'll just expand this idea. Right, squared, then minus 2 expectation d epsilon y f hat of x given d. Again, this is basically just expand this square, expectations over this, right? A minus b the whole square, you will get this, and then use the thought process that expectation of, let's say, x plus y, 2 random variables, is just the linear over them, right? These are all things you should be aware of. Then now let's say I will expand this term. Okay, let's take the first term. So this is expectation d epsilon. We know what y squared is, right? Y is basically f of x plus epsilon. So it's this squared I need to take. Now again, same thing I can do here. F of x squared epsilon squared f of x epsilon twice, right? Again, it's linearity of expectation. So I will get f of x squared expectation d epsilon squared and 2 times expectation f of x into epsilon. Okay, so any thoughts what this will come out to be?
F of x plus epsilon whole square.
No.
We're talking about
F of
this
x.
system.
No, you're saying what is this turn out to be? Means what? How are you going to only first term or the whole thing?
No. So the first term is what now? What will evaluate to be?
I think it is
It's
what
the
is
actual
it?
value. It's the
Is it
actual
MSE whole square?
Sorry.
F of x is the actual value, no sir?
Yes, f of x is the true value. That is correct. Some true value that it should be. Yeah. Okay. So does this value depend upon what training data I have obtained?
No.
No, right?
No.
So the expectation over D will just vanish away, right? Because there is nothing that depends on D here at all.
Yeah.
Correct? Now, does it depend upon the noise that is there in the sensor?
No.
No.
Right. Because the true value is something that doesn't depend on the noise by definition, right?
There is no noise.
So what will this turn out to be then, this expectation?
0.
We can ignore. No.
Okay, help me understand this in this integral. Okay, so integral y dx 0 to what is this integral?
Y square divided by 2 from 0 to 2.
No.
Oh, sorry, it is dx and okay, so it is only y into x 0 to 2.
0 to 2. So it's just y, some 2y, right?
Yeah.
So does it depend on x?
No.
So
no.
If I'm taking an expectation over this variable which doesn't depend on D and E, what will this turn out to be? Will it be 0 null then?
Yeah, it could be 0.
2y, sir? No.
Okay. How do we define expectation? What is the expectation of, let's say, x? If x is, let's say, continuous random variable, how do you define E of x? Is basically integral over x into P of x dx over all possible values of x. So again, these are all probability, notations. So somebody could have stopped me when I wrote this expectation. You know, we can take it even more slowly. That's not a problem, by the way. Okay, so let me do one thing. I'll just oh, it's already 6. I'll just give you the first 3 terms. Try the second and try the third term. Okay, today. First term, I tell you what it is. So basically, because this value doesn't depend upon these random variables, this turns out to be just f of x squared. Yeah, that's the way you write it. Now, what is this? Is basically again the noise doesn't depend on what data I have gathered till now, right? So this turns out to be just expectation over the epsilon random variable of this function, that is epsilon squared. Again, same idea here. F of x doesn't depend upon d or epsilon, so it becomes 2 times f of x into expectation of epsilon. Yeah. So then what I do is this becomes f of x squared plus this is, so expectation of any squared random variable is its variance plus its expectation squared. So because the e of epsilon is 0, this term goes away. It just becomes variance of epsilon, right? Now this becomes again same idea. This is 0, right? So this term vanishes. Now this becomes f of x squared plus epsilon, sorry, sigma squared, right? Because that's what we have assumed in the initial part, right? We said variance is sigma squared. Okay, so try to do the third term. Okay, and then basically the idea is this MSE, whatever MSE we were trying to calculate, this turns out to be something in this form. Okay, let me just get the final form for you. So sigma squared plus variance of f hat of x d plus f of x minus f hat of x d, this square. So if you see here, this is the variance term and this inside the bracket is called bias. So this comes as bias squared, sigma squared plus this is MSE. So basically the idea is if you try to decrease the variance, you will end up increasing bias. If you try to increase or increase the bias, you will end up decreasing variance, because this MSE is a constant number at the end of the day, because you're taking expectation over all possible randomness here. This turns out to be one number. So if you try to change this, you will end up increasing this. And see, try to understand this particular concept, variance of f hat of x given d. What does this mean? This is basically we're talking about, let's say, so again, see, this is a random variable where d is a random variable, right? So based on the training data, right, based on training data, I will expect some variance in the predicted value, f hat of x, right? This is what we're talking about, variance here. So now just think about two scenarios. If I have a simple model, if I have a complex model, what would this term come out to be? Okay, fine. So I'll close the discussion here. Any last minute doubts?
No, sir.
Okay. Fine. So I'll close the discussion for today. And I asked ma'am regarding the sharing of previous values. So previous alignments that won't be shared for now. Yeah. Okay. Fine. So we'll close the session here. See you next week, next Saturday. Yeah.
Thank you, sir.
Okay, thank you.
Yeah. Thank you.
Thank you, sir.
Thank you.
Thank you very much.